Hello everyone, welcome to the first workshop of JuliaCon and welcome to JuliaCon in general. If it's your first time or a 10th time or whatever, welcome. This first workshop will be particularly for beginners, beginner-friendly workshops. Our speaker is Matt Bauman from Julia Hub. He's the Director of Sales Engineering at Julia Hub, has 10 years experience working with Julia, super enthusiastic in promoting Julia, diffusing Julia, teaching Julia, and he will get you started in this amazing journey with, guess what, Julia. So Matt, the floor is yours.
Great, thanks, and welcome everyone. It's great to be here. It's exciting to be back at JuliaCon. You should have all gotten these instructions yesterday, I think, to install this. And the goal of this workshop is for all of us to be working with Julia. So I would love it if everyone would have a Pluto notebook up and running somehow, some way as we go through this. I'm going to be starting from zero as well and typing as we go. And I want you all to be typing along because that's the best way to learn. So if you've not gotten a Pluto notebook up and running, just raise your hand. Luca is going to be helping to get folks together as well. So yeah, like I want this to be a collaborative session. I'm going to be spending a few minutes here just introducing what we're going to be doing. So now's a great time to have others help you out, get up and running. So yeah, just raise a hand, just be like, hey, help. The goal for today is to get to know the language by doing. I want to focus a lot on mental models, how we talk about the language, how you think about the language, because if your mental models are wrong, you're just going to be surprised all the time, and it's no fun. And so the goal is really to think clearly about the mental models. And my mental model of this workshop is a walking tour. It is a group effort. We're all walking together. I've done lots of trainings in the past. And one of the things that I've often done is, come in with a script and we just kind of walk through it. I have all the things already written out on my computer and I just step over the code. It kind of means that I'm not walking along with you, right? And in a true city walking tour, the tour guide is walking with the group and you're going along with it. So this time I'm trying something different. I'm starting where you're all starting, which is an empty screen. And I think that should be a little bit more fun, a little more interactive. Walking tour rules apply. So what does that mean? What do you think of when you're on a walking tour, right? Like one of the things would be we try to keep the group together, right? That we don't want to leave someone behind. So if you feel like you're getting lost, shout out, say, hey, help me. Because if you're feeling lost, chances are someone else is feeling lost. Unlike a walking tour, I can't see where everybody is. I can't be looking and see that someone's around the corner in a back alley, took a wrong turn. So I want you all to be a part of that. What other things happen on walking tours, right? You notice things. You look around, you see different things, and you notice things, and you have questions. Ask those questions. Like let's spend time here. I have a route planned that will take through the language, but we don't have to stick to that, right? Like I've done lots of these tours. I know the language pretty well, and I'm happy going off my plan if there's an interesting question. And that's where learning happens, right? Is when you're engaged and thinking about that. Other walking tour rules: ask questions, be a part of it, right? Like see if you see something and you're curious about, ask a question. I know it's early in the morning, but how about this? Let's start off. I want to know where you all are, where everybody is to get started. How many folks have written 10 lines of code in any programming language? Okay, great. How many folks have written 10 lines of code in Python? 100 lines of code in Python? 1,000 lines of code in Python? Okay, we're Python programmers. How about MATLAB? 10 lines of code in MATLAB, 100 lines of code in MATLAB. Okay, cool. What other languages do folks know that you come in with a history of, like C, C#, C++, Java, R, nice. Rust, awesome. Great. So you all know programming, coming in with a lot of knowledge. That's great. How about Julia? I've written 10 lines of code in Julia. Some 100 lines of code in Julia. Yeah, okay, cool. All right, so we'll try to keep the group together. I want to make this as entertaining for everybody. So those of you who haven't written much Julia, I think that this should be, I've intentionally made this accessible to you and intentionally focused on folks coming from Python and MATLAB. That's my own history. For me, I've come from biomedical engineering is where I did my graduate work. And what I was doing when I discovered the Julia programming language was in a MATLAB laboratory where we had 100,000 lines of code worth of MATLAB scripts and stuff. Just an absolute headache, and I was constantly looking for something better. And Julia was it. That's how I ended up getting involved in the language. But I've also done data science in Python, and now I've worked with Julia for a long time, and I've gotten a lot of folks up and running with the language. So hopefully we can get you all up and running as well. So today's path. This is kind of the goal here. We'll see how quickly, how slowly we go through these things. I've practiced this a number of times, but I'm starting with 0 on my screen, and we can change how the path goes based on how folks are feeling. And I'll come back and kind of retrospectively look at what we're doing. I want to spend a decent amount of time talking about names. That's often where folks get tripped up in pretty much all programming languages I've seen, is naming is hard. There's a classic trope that there are 2 hard things in computer science: naming and something else. Whatever else you put in there changes depending upon who you're talking to. Cache invalidation off by 1 errors, all sorts of fun things. But naming is almost always one of the noted things that's hard, and it's because it's how we talk about things to each other, to the computer. We have to agree on what things mean in order to understand what's going on. So we'll walk through this. I have some exercises to work with. We'll break out. There is going to be a break at 10:30 to go back out, get coffee, and take a break. And at that point, you can also flag me down, and we can dig into any other questions that you might have. Do you have a question? Are you raising your hand? No? Okay. Sorry. Yeah, any questions or thoughts or comments before we dive in? Great. Let's do it. So I have an empty Pluto notebook up and running. And you should all have something up and running like this, right? And let's see, let's make this a little bit bigger. So the first stop on our tour is Julia as a calculator, right? This is pretty straightforward. You can do, 1 + 2. You can square things. You can, run all sorts of different expressions. Very straightforward, right? This is a very basic, but nice place to start. It is useful though to start thinking about, what do you want to do here? This should all be very familiar to all of you coming from other languages. You can also write functions and call them, right? And and do all sorts of things. Square root, all of these things are built into the language. Kind of one of the things that people often say about Julia is, whereas Python is a pseudocode for algorithms, right? The language is kind of designed to look like a pseudocode. A lot of people think Julia looks like a pseudocode for maths and, kind of textbook algorithms. And so often, you can just use it like a calculator and it works, and things just are the way you want them to be. The very first thing that you want to do, though, if you're looking at it like a calculator, is make an assignment or think about abstracting away, where instead of just using numbers here, you want to start looking at variables or names of things, so you can assign into things, and then you can look at x squared like this, and that works just fine. The interesting part about doing this in a Pluto notebook is that Pluto notebooks are reactive. That means that when you change a cell, it will automatically reevaluate all the other things that are there that depend upon that cell, and it has smarts to figure out what needs to be reevaluated. So I can change x here, and it will dynamically change this x squared block, and that is very useful, very interesting. It's a distinction from typical notebooks that you might be used to, like Jupyter. The big advantage of doing this is that your notebook, if all the cells look happy, then you know that your notebook is reproducible, because all the cells are up to date. They all have the latest information. And a Jupyter notebook is so easy to go back and change a definition and then forget to run some downstream function, right? And here, Pluto automatically does that. The one downside with it is if one of your functions takes a really long time to run, then you might need to be a little bit careful about, changing some definition that causes a 3-minute analysis to run, or something like that, right? That's not going to be very fun. What do I mean by if things aren't happy? Well, if I try to assign, introduce another name for X here and say, let's make it 4, it grays out this cell. And it grays it out because now I have 2 definitions for the same name. And Pluto isn't happy about that, because now which one is it going to use when it evaluates x squared, right? It needs to decide. So it grays one out. And I could click on these little 3 dots and say, oh, let's delete this cell. Maybe. Oh, I don't know. It doesn't want to delete it. You should be able to delete the cell. But I think I can just delete it like that by hitting backspace. That worked as well. Now my notebook is happy once again. The other thing that you should note here, I had one definition that became invisible. I'll talk about that later. I'm going to hide this for just now a moment. We'll bring in packages in a later session or later segment of the walking tour. Okay, so that's a little bit on the Pluto reactivity. We'll see more of that as we go down the path. Let's just start looking at, the, let's see here. Let me make sure that I have my notes here. Right. Okay. So let's start looking at, just a simple expression. Let's also define a y here. X and y are great classic names to use for very, like, something that you don't know about or something. And you can do like an x squared plus y like this. That works just fine. If I wanted to do this as a reproducible operation, I can introduce a function. I can say like, hey, let's make this a function. And a good kind of stand-in name for a function is the name f. I can say f of xy is equal to x squared plus y. And that just defines the function. It tells you a little bit of information about this. We'll talk about what that looks like in a second. But now I can evaluate that f. I can use the x and y that I have named here, right? And it gives me the same answer as 19. I can change, the arguments to, say 3.5 or something like that, and that'll square 3.5 and add whatever y was. And again, if I change y, it'll propagate all of these, change all my answers dynamically as I go through it. One interesting thing, though, is like now I have two different names here. I have the name of my argument and the name of, what is available to me outside of here. And inside this expression, right? So, for example, here I called f with 3.5 and y. So inside the f function, the first argument is 3.5. It's not 4. And if I look at what x is outside the function, it still says that it's 4, right? Outside the function, that doesn't change. The names inside the function definition here are like a different context. This is traditionally called scoping in many other languages. And it's the idea that you can introduce new names in different regions of code. And it's kind of like thinking about, thinking about how when I enter different rooms, people might call me different things. Lots of people call me Matt. That's a name that I'm very familiar with. But if I go into my childhood home, suddenly people call me Matthew. And it's just a different name, same person. It doesn't matter what name you call me. If you tell me to do something, whether it's Matt or Matthew, the same person ends up doing that action. Same thing happens here, right? You can think of the inside of a function as being a different room or a different context where you could define different names, decide you want to use different names for things. So that is kind of the basics of naming and such. I want to go back to my deck here and talk a little bit about naming a little bit more closely. So in the kind of playing around with things, I want you all to be playing and typing different expressions, typing different names, play around with them. We gave names to numbers as we were playing with it. The names that we choose to use for things can change. You can decide that you have a better use for the name X or a better use for the name Matt. Someone else might enter the room whose name is Matt and be like, oh no, that's going to be Matt. I'll be known as Matt B or M Bauman from here on out. So that way we can distinguish the two of us. So those things can change, but note that Pluto then reactively reevaluates the cells. So it tries to keep up with the changing landscape of what names you're using for things. Everything in a programming language has names and can have names. Yeah, go ahead. Yeah, so if you change the name in a later cell, yeah, sure, sorry. So the recording is what happens when you change a name in a later cell. The answer is Pluto will complain, right? If I try to, change what name I'm using for for something, it'll disable a cell. It'll say, hey, there are multiple definitions here. So right. So if I change, yeah. Oh, I see. If I change the name itself here to Z, then suddenly I'll get undefined errors. It kind of undefines the X and now there's no longer a name X in my notebook. So then suddenly I get errors saying, hey, this isn't defined. It happened here because you're trying to use X. There's no X defined in my notebook anymore. That's a great question. Any others? Yeah, it's a good point to stop and think about this. I want to be I'm trying to be very careful about how I talk about this, because this is something that, every programming language has its own take on, and it's all slightly different. And all programming languages try to do what you mean. And they do what you mean in slightly different ways, which can make things really confusing sometimes if you end up not quite understanding things. The other thing that I've often found people trip over is there's nothing magical about the names that we choose to use. The names that we choose to use are for us, not for the computer. We don't use a special name because it means something special to the computer. There are conventions that we use, right? So I played with X's and Y's. They're great and just kind of like arbitrary things to play around with. I's and J's are great loop variables. You'll often see those. Capital A, those of you coming from MATLAB will probably recognize that. We often use that in Julia world. What does that mean typically if you see a capital A in some definition? Yes, exactly. Often used as a matrix. But it doesn't have to be, right? It's just, these conventions that we're used to. We often use these shorthands, and we kind of assume that people know what they mean, or assume that people understand that these aren't special. And I think that often trips people up. I've seen lots of people get confused about that because, there's a lot of things. When you're learning a new programming language, there's a lot of new concepts, and it's hard to understand what the part that people are trying to teach is. And people try to abstract away and strip away the stuff that's not interesting, but then that stuff ends up being more complicated. So you'll see these things also. Capital X, often also a matrix. F's and G's are often stand-ins for arbitrary functions. Capital T, those of you who have touched Julia might be familiar with this, or other languages too, often use capital T as a stand-in for what? Yes, just an arbitrary type. And we'll talk more about types later. The one thing that I'll say here, and I want to say this a little carefully, is those of you coming from other languages, I find it most helpful to try to forget some of the things from other languages. So for example, those of you coming from C, C++, Rust, Julia's names aren't pointers. And if you try to use that pointer mental model, you're going to get confused. You can't take an address of a Julia name. There is no address of a Julia name. It's just a name. It's not really a box. You can't, you can decide to use a different name for the same object, for the same thing in the computer. But doing so doesn't, you're not like taking something out of a box or putting something in a box. It's a little closer to a my name is label, like if you want to use that mental model. I'm still not a huge fan of that mental model either, because the moment you put something tangible in your head about what a name is, the mental models can break down a little bit. It's really just a name. That's the best mental model I have for it. Just like a human name or a name of a dog or name of a pet, that tends to work well. I'll often use the word variable, but I don't even like that, because variable to me has a state that you can update, or it has like this mystique about it, like if you come from statistics, there's random variables, or if you come from algebra, there's unknown variables, or you come from other languages and they use variables. It's just such a highly overloaded word that I think that often it ends up getting in the way. And so if you think of assignments in Julia as just names, that tends to work pretty well. And yeah, like I said, name tags themselves, that's close, but I'm not a huge fan of that mental model either. But that's naming, right? And the way that we introduce names is with this equals operator. And that's yeah. So yes, go ahead. It's very, very similar. Oh, yes. How does this compare with Python? And the answer is it's really, really similar to how Python works. The one distinction that's most notable is Python doesn't introduce as many scopes as Julia does. And so a lot of, there's kind of context rooms that allow you to introduce or shadow names without affecting other names or like the global workspace. Python will tend to reuse the names more liberally than Julia will. Whereas, and so just like in this F definition here, it introduced a new room, a new context for X that allowed it to grab the name of the argument instead of the name of the global variable, right? That's the scope. Python does the same thing in a function, that's the same, but other constructs in the language end up not creating as many scopes as Julia does. But otherwise, very similar. And I've also followed Python folks who similarly say that they don't like the word variable when teaching Python for exactly the same reasons that I talk about here. The one distinction that is somewhat relevant also is that Python's names, they end up, you can kind of grab onto them in a slightly more meaningful way than you can in Julia. The names themselves exist in the program as a workspace or like a dictionary that you can look up and see what's in there, right? You can even ask in a function, what are the local names, for example, that are there, and you can reach in, change them, play around with them. That doesn't exist in Julia. And when you define a function, the variables themselves might get totally optimized away. They might not ever exist. We don't allow that kind of introspection. And so that's the other kind of big distinction. And it's one of the reasons that Julia is able to be fast, in fact, is, we don't expose the names as a first class object that you can grab onto like you can with a function workspace or the namespace of a module in the same way. Any other questions? I know this is really basic, but I'm happy to take time here because this is fundamental to understanding everything in the language. Everything's about naming. So what is plus, right? I used 3 plus 4. What's plus? It's a name. It's just a name. It's a name for a function. It's like that. There's nothing special about plus. And in fact, you can, I did 3 plus 4, that works. You can also change the way you do this. You can, let's make it a function call plus with 3 and 4. That also works. It's just a name. And so depending, and then I can also be like, what, let's create a new name called G and we'll set it to be plus. And now I can call G as a function of 3 and 4, and that will evaluate the same thing, right? This is all just playing with names. It's all, there's nothing special about almost anything in the language, which is a cool part of it. Yeah. Pardon? Good question. Can you do this, right? And the answer is no. The plus is special in that it can parse as an infix operator. So we use the word infix, can go in between two arguments like that. All other, there's a lot of symbols that you can use as infix and a handful of names that you can use in the infix position, but we don't allow that. In other languages, you might see some things like this, right, where you do ticks like that, or things like that. None of this works in Julia. It is, if you have a name, then it's if you're calling it like a function, you have to call it like a function with a parentheses like this. You also need the parentheses to be right next to it. If I have a space there, that's going to be a syntax error as well. You just can't put white space there. If you're going to use it as a function, you need that. And that's just to have an understanding of what this means. And the other interesting thing is, what can you use as a name? Well, you can use all the, we've played with X's and Y's. You can use any ASCII that you want here, right? That works. You can also use Unicode. And this is something that is kind of fun and helpful in many settings. And the way you write Unicode in Julia is with a backslash like this, kind of like LaTeX. And then you type backslash in the name that you want, and then you hit tab, and that'll bring up a tab completion box. And tab again will change it over to the Unicode that you want, and then that's your name. You can have numbers in names, but the numbers can't be the leading character. This will give you an error as well. So that just a little bit about the rules about what can and can't be a name. You can also use emoji. Smile, sure. That's a valid name in Julia, and you can use it in an expression, and that works just fine. Anything else on naming and the rules that go around that? Cool. So let's make this a little bit more interesting here. Let's start thinking about functions and control flow. So we have this function f, right? We defined f. Let's bring this down. I'll try not to move my screen around too much here, but I'm going to drag and drop this cell so we can look at it. I have x squared plus y, and I can start playing around with this 2.5, 2.5, right? That's going to give me some value. I can call it again with the same values. I can call it again with the same values. It blows up pretty quickly, right? It's squaring and adding and doing a lot of operations, and pretty quickly here it will it'll explode, right? It'll end up being too big to represent. We're 10 to the 30th now. Julia prints things out in scientific notation when it gets pretty big. And it doesn't take too many times here. Let's do a few more before we hit infinity, right? So I don't know, you can count the number of Fs that it took to hit infinity, which is what, like about 10. And if I wanted to think about this a little bit more carefully, I could ask, how many times do I need to call this function until it hits infinity, right? And this is where we can get into the control flow. So we can create a function, escape count, with and we have x and y. And what I want to do here is, ask how many times does it take me running this function until I hit infinity? And so how would I write this in Julia? Now I've suddenly introduced a new bit of syntax that you've not seen yet. You can define functions like I did before with just like this assignment, right? That's giving me a name f that takes 2 arguments, and you can call it like a function. I can do the exact same thing here with the keyword function. This will introduce the name escape count, function of 2 arguments, and then I can define what happens on the inside here. So I'm going to want to square x, add y, and I want to ask, did that hit infinity, right? Did that end up going to infinity? And how would I do that? Or what I want is actually the count of times that it took in order for me to hit infinity. So maybe I want to do a while loop, right? We could just say result is x squared plus y, while the result is less than infinity, we can do something, right? We can update the name of result is equal to x squared plus y, right? But that's not going to quite do what I want, right? I want to evaluate this number of times. I want to update x, right? I want to what I'm doing here when I'm reevaluating f over and over and over again is I'm passing the answer, to x squared plus y as x again and calling it again and again and again. So what I want here is to update x itself is going to be x squared plus y. So maybe I want to change this around a little bit. While x is less than infinity, we will square x, add y, and update the name that we're using for x like that. That will just, so if I do this, right, and have this escape count thing here, and I do escape count for 2.5, like I ran before, it's just going to run and nothing happens. I get no output here. Why didn't I get an output? Well, it's because I didn't return anything. I just ran this loop while x is less than infinity. I squared it and added a bunch, and at some point it hit infinity, but I don't know when, right? So let's restructure this a little bit. The key part here is I want the count of times that it took in order to hit infinity. And so instead of a while loop here, which should be familiar to all of you coming from other languages, we can use a for loop. And so for, let's use I as the variable here for I in 1 to, let's say, 100. We'll do this. And now we can ask if x yeah, sure. We could ask if is inf x, then we'll return the value I, right? So is_inf is just a name for a function. If you're ever curious about, what functions exist or what they might do, you can go down on Pluto. There's a live documentation, and you can, select a thing. I happen to know what functions are available. If you don't know what functions are available, you can, search for things. You can ask. There's all sorts of ways of looking things up, and I'll point to some resources towards the end about how to do that. This is just a little bit of magic that I know, right? Is_inf is a function that's available to me to use, and it just asks, is that number infinite or not? So if x ends up blowing up, let's return the count of times that we squared and added things, and that will return I. Now we can again run this, right? And oops, I need to evaluate this cell, right? And now we get, it took 10 times to explode up, which is good. I said that was about 10 Fs. I didn't actually count them, but I guess that is the right number. So it took 10 squarings and addings in order to hit infinity there. What happens if I change this number to, say, 0.25, right? And we run that 11 times, 0.25, and suddenly I get nothing again. What happened? Why did I get nothing? Any answers? What happened? What did I do wrong? Yeah, exactly. It took more than 100. So what happens if I fall off the end of this for loop? Well, we'll probably want to return maybe 100 plus 1 as a stand-in for, took more than that number of iterations to happen. So that works. This is, a nice introduction to control flow. I've introduced while loops, right? That straightforward. You should be familiar with that. I've introduced a for loop here. It uses this special in. It gives me the name I inside this for loop that I can work with. I've introduced the return keyword, which breaks out of loops and gives me values, and at the end I've returned things. And in general, the return command here is optional. You'll also see people do things like this, where just the last expression that's run is going to be used as the return value. And so I personally like the style of having returns here, but it's a style thing. Inside this for loop, that's important, right? Because I want to break out if I, have, say, let's make this bigger so it breaks out quickly, right? If it only took 9 iterations to hit infinity, I want to break out, stop. We don't need to keep going. We know that we hit infinity. So this is, how control flow works in Julia, very familiar to all other languages. Any questions on this slightly more complicated definition? Yeah. Correct. Yeah, so the question was this range syntax I also introduced, this colon syntax. It's what does this do is a good question. What is this? And if I put it in a cell by itself, it just prints out like what you put in. And this is a pretty common thing in Julia, where if you're ever curious about something and you type it in and you get back exactly what you typed in, which is can sometimes not be helpful, because it's like, well, yeah, I know that that's what I typed, but what is that? If you don't understand what that is, it's not actually helpful. And again, you can do some, if you highlight the part here and pull up the live documentation, you'll get the documentation for it. And in this case, it's the colon operator. Again, what is this colon? It's just a name. It's just a name for something. And in this case, it's a name for a function. And it is a symbol, so it can be used infix. I could put spaces around it, just like I had put spaces around my plus. It'll print out without spaces because that's kind of the standard style that we use for Julia. I can, of course, not just use numbers here, but I could put my x in here, and it'll grab whatever the value of x was and give me 1 to x. What does it do, though, is an interesting question, right? So what is this thing? I'll name it R so I can play with it a little bit here. R is kind of a typical word for what we end up with here, because it is giving me what we call in Julia a range. And so we'll use the lowercase r to talk about the range. I can, what kinds of things can I do with R? I can ask for what's its first value, gives me a 1. I can ask for what's its last value, gives me 100. I can do other things with it as well. I can index into it, or actually let's ask for its size is a good one. So, or in coming from MATLAB, this will be familiar. You can ask for a size of something. Coming from Python or NumPy, this would be like asking for a shape. And it's just going to say that it has 100 elements, because it does include the endpoints here, 1 to 100. I can also index into R. So I can grab its second element, and we use square braces to index in Julia. And this is treating it like an array. So these are all different ways that you can work with these values. I can change its definition, and then, of course, the second value will change. And notably, of course, the first value is going to be the first value of the thing. We don't use zero-based indexing in Julia. It'll give you an error saying that it tried to access something that had 98 elements at an index of 0. And we use one-based indexing. There's a whole diatribe I could go into about which one is better. The answer is depends on what you're doing in many cases. And in my use cases, I like one-based indexing a lot. but that's a whole aside. So that's on ranges. And when you have an iterator, or when you have a for loop like this, it's going to iterate over whatever you put in the right-hand side of this in operator. And you say, for I in, this range is very common to happen here. But what happens, what you put on this right-hand side can be whatever you want. It could be a range operator. It could also be, an array that you write by yourself, right? 1, 2, 3, 4, and that works just fine as well, right? And this will just take values successively from this array. Doing 1 to 100 is kind of like defining an array that has all the values 1, 2, 3, 4, all the way up to 100. Nice short one. And it's also much more efficient. Great. Okay, so that's my here. Now let's start thinking about how we would understand this function, or think about a little bit more of what this is doing. Well, let's make this a little bit more like a real world use case. And maybe 100 isn't enough in some cases, right? Like when I was doing, 0.5, say, oops, that's not valid syntax. 0.5, 0.25, it, blows up at 101. We didn't use enough iterations. I could, give myself more iterations here. Let's make this a little bit bigger. There we go. Too big. So you can play around with, where is the interesting part here? Where does this end up being interesting? But every time I change this, I also have to change the value at the end, right? So that didn't blow up. You can kind of try to figure out, where does this get interesting? Where does this end up being interesting? Oh, there we go. So at 0.5, we end up, being slightly more. If I'm slightly over 5, then now it took over 1,000 iterations again, and I can add another 0, and you can keep going, right? And it'll, okay, so that took over 1,000 iterations, 1,017 iterations when we had 0.5. But I'm needing to change both of these numbers at the same time. It's kind of a bad code smell. One thing that I might want to do is say, well, let's call this my max iteration count is 10,000, and just use that twice, right? So that way I don't end up accidentally forgetting to update that cell and reevaluate it. And that gives me the same answer as what I had before. And again, I can go in and look. Oh, now I've hit 10,000 again. We're over that count. So maybe I want to do 100,000 it loops, right? And now it's slightly over 100,000, or slightly over 10,000, I'm sorry, iterations that it took. And doing actually a decent amount of math each time to figure out this, but I'm keeping to need to redefine my function every time I do this. Maybe what I want to do is pass this as an optional argument. So I could say my max iter, and we can give it a default value here of 100. I introduced a little bit more syntax. I used a semicolon here. So whereas before, when I've introduced functions, I've used comma separated lists. Now I added a semicolon and a name here. And what does that mean? Well, if I try to add a third argument here, so let's do that 100,000 iterations, this will say, oh, we have an error. It doesn't work. And that's because I didn't use a comma here. I used a semicolon, which introduces this as a keyword argument, which means that I have to pass it as a named argument. And the way to do that is by saying max iter equals this. It's worth taking a moment and looking at this method error. It this is something that a lot of beginner Julians end up seeing very frequently, is a no method matching error. And it's worth looking at what is happening and taking a second to understand this, the syntax and how this reads, because if you can understand the errors, you can understand how to fix them. So when it says no method matching, you can see it's calling the function named escape count with 3 arguments, and it uses these double colon syntaxes, which I've not introduced yet, but it's a shorthand for saying the types of things. So we have 2 floating point values and an integer value, and it gives me the stack trace of the value of what I called, and in Pluto it hopefully prints out exactly the code that I had written. So I had 3 arguments, floating point, integer. The error message itself gives me a closest candidate. It says, hey, maybe you meant to call escape count with 2 variables, and the any here is also a type. It just means that it could take anything. It effectively says that, I defined this without putting any types on it at all, and with a semicolon max iter. And what that is saying is that this is a named variable. So let's go back down here, and I can name it in my function call and pass it as a keyword argument. And so this will be very familiar to those of you coming with Python. You can have keyword arguments like this that just pass their values by name. The distinction with Python is that in Python, they conflate positional and keyword arguments. Positional arguments can be passed as keywords. Keyword arguments can be passed as positionals. You can mix and match to your heart's content. In Julia, we don't do that. We care about whether the function was originally defined as a positional argument or a keyword argument. So you have to match the definition here. So in this case, I had 2 arguments that were positional. 1 argument was a keyword value, and I have to call it like that in order for it to work. Okay, so that is this. Now, how might I start thinking about, so when I was playing with this, I was like, where is the interesting part? Oh yeah, go ahead, question. Yeah. Yeah, we'll get there. Good. That's an awesome observation, that in the method error, that kind of looked like you could have multiple argument or like different combinations of arguments or different ways of calling a function. And my answer to that is just, yes. And we'll understand that in just a second. I want to get to that point. So yeah, and you can also see that hint here when I define functions. It says that there's 1 method. It kind of gives you a sense that you can start adding more methods to functions as you work through them. So this is yeah. I want to hold that thought. I won't dive in quite yet because we'll get to that point. Right. So I was thinking about how we might introspect this, but I think let's go back to my slides and just talk about functions, because they are, oh no, I wanted to do one more thing. I'm sorry. I had one more thing that I wanted to do, which actually does connect with that question perfectly. And that is the ability to define multiple methods within the same function. So if you remember, we had defined f as being, x squared plus y, and it has a generic function with 1 method. What if I wanted to define a function with just 1 argument here? What would f of x be? Maybe f of x squared plus x, like this, right? So now I have 2 ways that I can call f, right? One is, take the first argument, square it, add y. The other way is take the only argument I passed, square it, and add x itself. So I can call f of 2.5, 2.5, and that will give me 8.75. or I can delete that second argument and it'll give me the same answer, right? Because X and Y are the same in this case. And now you can see that I have a function with two methods. I've added an extra method to my function. And if I try to call it with 3 arguments, now I get a method error again, like we had seen before, where there isn't a method for 3 arguments, but there is a method with 2 arguments. Maybe that's what you wanted, and that's closer than the method that only takes 1 argument. So it doesn't give the 1 argument method as a hint. But you can ask, what are the methods of the thing that we're calling f here? And it says that there are 2 methods, and they're both defined in my notebook in different cells. And you can, it's a little bit, Pluto has this a little bit gibberishy about how it defines them and where it is. But you can see there's f of x, and then there's also f of x comma y. So the other thing that I can do here, though, right? So this is a kind of a common thing that these 2 methods that I've defined. The one is x squared plus x, the other is x squared plus y. I can also add a optional, or like I can simplify this by saying y, let's give it a default value of 2.5. Let's delete that and do this. Whoops, we have still have the 3 argument call here. Okay, sorry, my screen's jumping around a little bit. There we go. So we have this f as a generic function. We have a default value of 2.5. So if I call, f of 2.5, it's still squaring 2.5 and then adding 2.5. If I call f of 3, it's squaring 3 and then adding 2.5. That's the optional argument here. It kind of looks like a named variable, right? It kind of looks like a named keyword argument, like I had done with my escape count here, except instead of using a semicolon, I used just a regular comma, which says that it's a positional argument that's optional. How's that ending up being defined, though? It's actually defined exactly the same way as what I had done in the first place, right? It is defining a function with 2 methods for me behind my back. It's kind of saying, okay, this is the same as saying f of x comma y is equal to x squared plus y, and simultaneously defining f of x is equal to x squared plus 2.5, right? So if I only pass it 1 argument, we'll do this. Actually, it's a little bit more succinct than that. It's calling f of x with 2.5 as the positional argument, right? So if we have, it does this behind my back, as you might say, right? It's just a little bit of syntax magic that automatically defines 2 methods for me that take different number of arguments, and we can use it this way. So that's defining functions and stepping through them, and having multiple methods is useful in many cases, right? This is a really simple math expression here, but we'll get to making this a little bit more interesting in a sec. Okay, so let's take what we learned and we can actually do this one better and set a default value of y as being x itself. This also works. This is slightly different than what would happen in Python, where the x comes from your outside namespace, and Julia uses whatever came from before in the argument list. So I can define a default value of f of the second argument as being whatever the first argument was passed. And again, this is the same as passing an x here, right? So we have a 1 argument that just squares x and adds x to it. The 2 argument gives me this, and so now, if I do 2.5 comma 2.5, that gives me 8.75. Maybe let's do 3 and delete this. That'll be 3 squared plus 3 is 12. Straightforward enough. I can go down here to my escape count and say, well, maybe I want to also give a default value to y, and that'll just give me a second method. Same thing. Now I can, delete my second argument here. It still can take that optional argument of my max iter. And now, of course, if I have this, my breakoff point is different. 2501. I think that's my interesting point, right? And you can play around with what this value is. So how might we understand what this escape count function is doing? Well, one way to do it is just by what I'm doing here, right? By playing around with the numbers I pass into it. I can see what's interesting, see where the interesting values lie. Look at it this way. The other thing that I can do here, and I want to do this a little bit carefully because it does affect the notebook itself, is we can bring in other packages to bring in more. I'll get to you in a sec. We can bring in other packages to get to more functionality. And the package that I want to do is, how do you understand what a function does? We can plot it, right? Julia is a great numeric language. It has great capabilities. So let's bring in plots to do this. And when we do this, I'm also going to bring in a bunch of other packages at the same time. The way you bring in packages is with the import keyword. And let's bring in plots. Let's also bring in a bunch of other packages at the same time. So I want you all to type in this somewhat convoluted statement all at once, because it's going to take a few minutes if you've never run this before. And I want to do this, and then I'll take questions and kind of wrap up the function section while this is running on all your computers. So I want plots, I want Pluto UI, I want colors, I want images, I want CSV, and I want data frames like this. So these are the functionality that I want to use. Let me make sure I have them all. Yeah, that's what I want to bring in. So type exactly this. Case matters. So Julia is a case sensitive language, especially when it comes to packages. The names of these packages are all case sensitive. And when you run this, it may take around 2 to 5 minutes, to kind of depending upon the state of your machine, or it may take a second if you've already done this. And if you want to play around with it as it's running, you can see the status window. We'll give you some updates on what it's doing with package management. So you can all type this line. This is an important one because it'll set the stage for everything we do from here on out. And hit enter, then it'll start running, and you can see where that goes. So now I'll take questions while you have that running. Yeah. Yeah. Yes.
The optional keyword argument doesn't do this.
Correct. Yeah. So methods are defined by their positional arguments, and they optionally have keyword arguments. So the method itself, has the capability of taking keyword arguments. It doesn't actually affect dispatch, which gets a little bit more advanced, but in short, you can kind of think of a keyword argument as, I like using keyword arguments that kind of change how you work with a function, and not what the function works with, if that makes sense, right? And that's exactly what we did here, right? The max iter is kind of like a higher level parameter of what the function itself is doing. It's not changing the data that the function takes in, right? It's kind of a option and that's how keyword arguments are often used in the language, and so it kind of works nicely to think of it as a kind of like an annotation or like a tag along sort of thing that comes with a method. Yeah. Yeah, so if I didn't define this didn't give a default value here, then well, let's do that, right? So I can hit enter, and this escape count function works because I passed in max iter. If I don't pass in max iter, it gives me an undefined keyword error saying, hey, you didn't assign max iter. So yeah, this makes it, just by not giving it a default value, gives me it gives me the ability to make it mandatory. Yes, exactly. The semicolon is the magic that makes it a keyword argument. It's not what makes it mandatory, it's what makes it keyword. So in the same way as, when I defined, simple functions here, right? So f of x, the comma here is making it a positional argument, and this is now an optional second argument with the default value of whatever the first argument was. If I didn't have an equals, then it's a mandatory second argument, and I only define one method. It's kind of similar with the keyword argument. The semicolon just kind of distinguishes between positional and keyword. Yeah. Oh, if I just did escape count like this and a colon and 100 like that. Oh, when I define it, like you would put this like. Oh yeah, so I could do the same thing and put max iter down here. Is that what you're asking? Yeah. Oh, I could do it as a, yes, I understand now. You're talking about changing the semicolon to a comma like this? Yeah, yeah. That works, but then when I call it, then now it is a third argument, and it needs to be positional. So then I can only access it as the third argument. So I would have to do 251 and 100 like that, right? So now this is my third argument. I can't pass 100 like this. That doesn't change my max iter, it changes my y. Right? So the positional arguments are always going to be, this is the first argument, this is the second argument, and the third argument is my max iter. So if I make this 1,000, it doesn't change the number of iterations, it's actually changing the y, right? Or 100,000, it's blowing up faster, not giving me more iterations. That makes sense? Yeah. Yeah, exactly. So it's just the choice that you have when you're defining functions. We'll go back to my keyword argument. There we go. Okay. Yeah.
Instead of applying in one variable, that changes in the function.
That's a good question, right? So the question is, what if max iter in here changes, right? So if I decide to set max iter to 10 inside my for loop, what ends up happening? And that's a great question, right? So now, what happens? Do I do 100 loops or do I do 10 loops of max iter? Does it affect what's happening here? And I can kind of play around with it, right? And see what ends up happening. I'm not quite sure what is happening. So you can see here, okay, yeah. So if I, do, let's say 2/8, right? That takes 25 iterations. It returns so we're doing more iterations than 10, right? So it is actually continuing to go on. The reason for that is because when you enter the for loop, it's evaluating this at the beginning. You can kind of think of it as doing this, right? R is equal to 1 to max iter for I in R, this is equivalent, right? It's defining our range. It's then looping over that range. And now we're changing the name that we want to use, or like deciding we have a better use for the name max iter. And we're going to set it to the value 10. It doesn't change what this R was, right? It doesn't go back and retrospectively change that. And it doesn't retrospectively change the number of loops that we end up stepping through, or the number of iterations we go through in the for loop. But what it does end up changing is down here, we're also using max iter, right? And we've decided that we have a better use for the name max iter, and it's going to be equals to 10. And so when we, hit the end of our road, we end up with 11 here. This gets a little bit more obvious. Maybe if I do this like negative 2000, right? It's not affecting the number of iterations that I run, but it is affecting the name itself, max iter. And when I use it again later down in the function, it's using that updated state, or that new value that we're deciding to use there. Mm-hmm.
And instead you have in one to a variable, and you have the variable at the end. What happens then?
So like let's go back here. So the question is, what if the range here is like 1 to n, like this? Yeah, so if I then say n is equal to let's say a random integer. Let's do random some value in 1 to 10 here. This is a function that I can call, and let's look at what that does here. So random from 1 to 10 gives me just a random value, just something interesting, right? So if I put n inside here and I try to run it like this, it's going to say, well, n wasn't defined when I entered that for loop. Is that the question that you're after? Or like, I don't know that I quite. I see. Right. So I don't quite. Yeah, maybe like. But the problem is here. So you want the max iter. Yeah, I don't quite understand the game that you want to play with this one. Oh, so I understand. So like if you, okay. So yeah, you want to increase max iter if I ran out of iterations here, right? So let's get rid of this. So like what I could do is I could return escape count x, y, and max iter times 10, right? Max. Yeah. This is going to be a little bit crazy because it'll never terminate, right? Because it'll always rerun the function. But this works, right? You can do it like this. Maybe if I see, why is that? It's still giving me an n not defined. Why is that not? Oh, did I hit I think I hit an infinite loop. Right, because it will loop infinitely if my escape count is not big enough, right? In this case, 0.25 doesn't actually escape. And so I have hit a infinite loop where this will just loop infinitely, right? It'll keep going and for forever. It'll just keep increasing the number of iterations. And that's why I'm having trouble. Let's see here, if I how can I think maybe if I, yes, I want to interrupt the notebook. Sometimes interruptions can be a little scary. Let's see if I can do this without, there we go, great. So, yes, awesome. we've escaped the infinite loop. Escape count 0.5, say. So this will work as long as I don't end up with an infinite loop. I could, great, as the comment was, this might as well be a while loop at this point, right? It'll never terminate. But yeah, if I wanted to set max iter to be bigger, right, like equals max iter times 10, and then redo the for loop, I could do that, right, just by copy and pasting. That works. Or I could call the function again, or I could, do other things, but yeah, sky's the limit. You can recurse infinitely. It'll just loop infinitely and never terminate. That's fine. It's not, yeah, you'll eventually, if you're recursing, you'll end up with a Stack Overflow at some point. We don't do tail call recursion optimization, if you're familiar with that.
Yeah.
But yeah, so probably if I would have let that go, it would have eventually hit a Stack Overflow. But it probably would have taken too long to hit that point because I was increasing my number of iterations tenfold and getting to billions of iterations far more quickly than I would exceed the stack space of my computer. So it's just going to loop for a really long time in this particular case. Okay, so let's go back and kind of recap functions. We've talked about context, which is scope. We've talked about names. We've talked about arguments. A good question, though, is what is actually getting passed? So I call, this escape count with numbers. I call it with x's. What is that function receiving? This is a little bit of a conceptual question that doesn't have a terribly good answer. Any stabs at it? Like, what do you think Julia is passing when I call a function? Nothing. It is, but when I change the values, it's evaluating it and getting different answers. The best way to think of this is it's passing the thing I'm passing, like the thing itself. It's not passing names, right? It's not giving me a name. When I change the name inside a function, it's not changing the names outside of the function, right? There's different groups there. It's not passing pointers. It's not passing references. Best thing to think of here is it's passing whatever you're sending in itself. And we'll look at what that ends up. It gets a little trickier when we start changing things, but that gets us, towards where we want to be. Some languages call this pass by sharing. I find that terribly confusing. The best way to think of it is just like there are objects or there are things in your computer that we have names for, and we're passing those things, those objects, those the values you can think of. It's passing whatever it is. If it's changeable, the function can change it. If it's not changeable, the function can't change it. And playing with names doesn't end up changing the names that you've used elsewhere because it's a scoped operation. We talked about positional arguments and named arguments, the keyword arguments. All of these things are just methods and kind of annotations on methods. So before we get to our break here, which is going to be in 10 minutes, let's look a little bit more closely. So we've added that import statement on loading all these packages. Let's change, or let's go in and let's grab some names from these packages that we've loaded. And I'm going to grab the plot function from the plots package. So when I hit that, when I did import, I only got the package name itself. I can grab, functionality that comes with the packages by using this special colon syntax. This is different than the colon that you saw before. Defines a range. It's just it's kind of like saying from plots import plot. If you're familiar with NumPy, right? It's kind of grabbing a single name out of this. And now I can do a plot function where I can plot, 1, 2, and 3, and the values 10, 20, and 30 like this. And that gives me a graph. Straightforward. When I did this, I introduced these square brackets. That's an array, right? So I can change the values that I'm passing in here. So 1, 2, 4, 10, 20, 30 gives me a bendy line. I can also pass in the ranges that I've defined before, right? So X value of 1 to 3, and the Y values are 10, 20, and 30. And this kind of gets me towards talking about arrays now as well, right? So we are looking at collections of data. An array is just a group of numbers that are in a list or a sequence. And so a range like this is itself an array. The square brackets defines an array. And you can call it as a function, we're passing them as function arguments to the plot function, which plots what we have here. So that's arrays and plotting. Of course, I can also, do other values here, right? So this could be, 0.4, comma 30, right? Give me a broken line. I can pass in other things here, or I can try to figure out what my escape function is doing, right? So I can look at the values of, so I can evaluate my escape function. So my escape count, I can look at what happens when we pass 1. I can look at what happens when we pass 2. It's just going to blow up, right? These are big values. I can look at what happens when I pass 0.1 or 0.2 or 0.5, right? Like you can just see what ends up happening here. What if I wanted to plot this, right? Well, one thing that I can do is you can actually plot functions themselves. I can pass this as a variable here, and I can plot the escape count. And the plots itself will define what's happening when I do this. This is kind of an interesting question. It is by default just saying, I don't know what you want out of this function, but I'm just going to test it at a bunch of different values from -5 to 5 and see what answer I get back. And it is just going to use it as an argument of one value, right? So we're just looking at, escape count of -2, -1, 2, 4, things like that, right? It's just passing those values. And this is what I end up with. So you can kind of start seeing where the interesting parts might be. Now, I could go in and ask, so I want to look at the escape count at some of these things. You can see like maybe this section is the interesting part. I could look at a bunch of values from like maybe 0.1, 0.2, 0.3. Let's evaluate escape count at that value. So let's say for value in there, let's look at what this is. And I run that and I get nothing. And that's because I'm not doing anything with this, right? I'm evaluating it, but I'm not seeing what's happening. How could I see what's happening here? One way I could print it out. You can say print line as a function you can call. It's built into Julia, and it will print out the values successively as you go through. So you can see, you know, 0.1, it hits the max iter. 0.2, it hits the max iter. 0.3, it's 21. And here I'm evaluating this as ranges, right? But I'm printing it out to my screen. How else might I look at this? I could store it. You know, I could store it in an array itself, and one way to do that is by kind of turning this on its head, and instead of doing the for loop and printing, I can create an array where I call escape count on value and put the for loop inside my bracket notation here for value in 0.1, 0.2, 0.3, like this. And now, instead of printing out the numbers to my screen, I am getting back an array of integers from, you know, that gives me those values. And that means that now I can pass this to a plot, right? Because it's an array. So 0.1, 0.2, 0.3, like this. I do my that gives me starting to look at this. But now I could think, well, maybe it's better to define this as a value called x's, like my x-axis, or yeah, maybe let's call it my x-axis. It's going to be 0.1, 0.2, 0.3, like this. And now let's plot my x-axis, and the second argument to plot is my y-axis, which is just going to be, you know, this array of escape count of value for each value in my x-axis. That's the same thing. Now I can make my x-axis bigger. I can start looking at, you know, more things. Let's change this to be a little bit, you know, instead of defining this by hand with you know, points that we put here, we could use a range operation, right? And we had talked about ranges like this, you know, 0 to 10. Well, that doesn't give me anything interesting at all, because, you know, it avoids the interesting regions. What about if I add one more term here to this colon? I could say I want to step by 0.1, for example, right? And now this gives me the values 0 by stepping by a tenth to the value 10. And so this is the same range syntax, just as 3 arguments now, where the middle argument is my step. And so let's make this a little bit bigger, right? You can zoom in now on my interesting part, 0.3 perhaps, and 0.25. Right, you can go and see like where does this get interesting, and give myself more values, a smoother curve. We can make my max iter bigger, right? And you can kind of play with this more and more as you go through. And you know, there's all sorts of fun things that you can do, but this is still a little unwieldy, where we are looking at this. And the last thing that I want to introduce before we go to get our coffee break is the idea of a succinct way of evaluating lots of values at the same time. So if I wanted to look at escape counts over all the values of x-axis, this is, you know, one way to do it, which is this, you know, in the square bracket notation to create an array explicitly. And this is called a comprehension, an array comprehension. It's very familiar to those of you coming from Python. It's, you know, a nice concise way of putting a for loop here and just getting a value and plopping it in an array for you as you go around, go through each iteration, just like a for loop, but creating an array instead of doing some execution. Now the interesting part here is, what happens if I didn't do that? What happens if I just tried to call escape count on the whole x-axis all at once? I can try it. why not try it? And we end up with a method error. And this is, again, an interesting point here. Where did this end up happening? What this is, like I had said, you often end up seeing this as you learn Julia. We end up with this wild no method matching with the crazy types and some weird things that are that are going on. It's kind of hard to read, right? There's it's the exponentiation function. It's trying to exponentiate, which is kind of funny too. You can see what's happening, and it tells me where that happened in my escape count function on line 3 when I tried to square x. And why didn't that work? Well, it's trying to square what I passed in, which is my x-axis, right? It's trying to do x-axis squared, which is the same method error, right? It's saying you can't do that. It happily passed the x-axis to my escape count, but then once I got into it, I ended up with an error when I tried to square it. You can't square vectors. You can't square lists like this. So how could I do that? And the answer is, well, I could do the explicit value for value and blah 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 blah, or much more concisely and much easier is to put a period in front of this function operation. And that's going to do what's called broadcasting, or a pointwise operation, where it is exactly the same in this particular case as doing this array comprehension, only way more concise, way more simple. This is we'll talk more about this after we all get coffee and stretch our legs for a moment. But it's doing exactly this. So I can update my plot here to just do the escape count on my x-axis like that. So that puts us in good shape for the second half, where we will dive in deeper on, well, let's go back to our path. So we've gotten through the first 3 things. I didn't talk about mutation. I skipped over that to talk about control flow, arrays, and plotting. Now we're in good shape to talk about broadcasting colors and images. We'll come back to mutation. So I skipped this one line here, just based on how this path went. But when we come back, we've actually covered a lot of good ground here. We'll talk about broadcasting colors, images, and get some exercises for you all to do. So yeah, let's go stretch our legs, get some coffee. Yeah, and yeah, I'll come around and yes. What do you want?
Where is the Teams?
The teams.
There should be. It should be showing. We need to have visual check that transcript is there.
Yeah, transcript.
Nice.
Something went wrong.
No,
Oh, there it is. Great. Great.
Good to go midway. No, I have peace of mind.
Already.
I think that it's been shot.
They will, yeah, exactly.
Ja. Ja, laat me gewoon dat is goed ook. Ja, ja. I don't know if it's already done. Oh yeah, we would love to.
That's fine.
We're done for 15 minutes, like, you know, Russian. Oh, God, will hurt.
Yeah, I'm running this on Julie. So I can actually make this entire notebook available to make the voice look. I share it, and I think we can have. And slides are 5 or 6 slides. We can each of those as well, and then we think Rhonda or we don't, so it's all worked out. And it's that we can have these lines there as well. All right, great. Hopefully everyone's feeling a little bit more refreshed. Let's see where we were. Right. So what we had just done here was introduce plotting, and brought this idea of this dot operation. A good mnemonic for it is a pointwise operation, right? It's evaluating a function at each element of an array. And let's do one thing before we go a little bit farther here, which is to change our escape count function and start talking a little bit more about types. So one thing that I don't know if you've noticed yet, there's a little quirk that is kind of funny about our function, which is that if I run it at 1.0, I get a value of 11, but if I run it at a value of 1 without the 0.0, I get 101, which is a little funny, right? Like, why am I getting different answers for the same, what seems to be the same value, right? Like, why do I do this? And we can actually make this even stranger yet, where if I use a scientific notation, so you can enter code in Julia using scientific notation, like 3e e10 or 3e8, right? Like 3 times 10 to the 8th is scientific notation. It prints out like that. If I do a smaller number, it'll print out without the exponent there, right? 3,000 is 3 times 10 to the 3. This e is scientific notation, and right. So I can enter this 1 in scientific notation as just 1 times 10 to the 0 is going to be 1.0, right? So I can do the same thing here. That gives me a value of 11. I can also do it with, instead of an E, you can also enter this syntax with an F. And similar, just like I was saying with ranges, it just spits back, just like I wrote it in. But if I put it here like this, I get yet a third answer, which is confusing. So let's start talking about types, right? So we can ask what the type of 1 is. This is calling a function named type of. It's an int with 64 bits. I can ask for the type of 1.0. It's a float with 64 bits. I can ask for the type of 1e0. It's also a float with 64 bits. I can ask for the type of 1f0, and this is a float with 32 bits. So coming from other languages, singles, doubles, double precision, 8 bytes or 64 bits. Those are all things that you should be familiar with, right? And they're all representations of the same value, right? There's also type of 1. They're all this integer, and they're all equal, right? 1 is equal to 1.0, and that's true. This is a comparison now. Instead of introducing a name, you're asking, are these two things the same? Well, they are the same, but then if they're the same, why does my escape function or my escape count function at 1 give me a different answer than at 1.0? And why is that different than 1.0f0? Any thoughts on why am I getting 3 different answers here for the same values of the same inputs? Yeah.
Safe index kind of like, so for float 32, that's quite much lower than the float 64, and float 64 can also just have a lower value than the int 64 as the max value.
Yeah, exactly. So the answer was infinities are different based on types, right? And that's exactly right. So going back to our escape count function, we had used this isInt function to ask, did we blow up to infinity? And if you think about isInt of an integer value, well, you're never going to get an infinite integer value, right? There's just not an infinity represented in an integer value, so we will never hit infinity here. And in fact, if you look at what the definition is for isInt for integers, it's just going to be return false. Like it doesn't need to do any computation. It just knows that for integers, we're not infinite. It's, you know, you can't store an infinite integer in a computer, whereas floating point variables are floating point, and so they have a representation of an infinity. So maybe we need to change our escape count function. And maybe what makes more sense here than asking, did we blow up to infinity, which varies depending upon the types we use, which isn't a great, you know, that's not a great thing to have happen. You want to have your functions give you the same values for equal inputs, and the precision at which you're working shouldn't fundamentally change the algorithms. Like maybe it should change the precision of the algorithm, but it shouldn't change like answers like this. So, you know, maybe let's say instead of if it blows up to infinity, like once we get to a certain size of X, it's going to escape pretty quickly, right? The interesting stuff is happening around, you know, 0.25, or, you know, when we were looking at our plots, right? That's where that slope was. So maybe let's just ask if the absolute value of X ever gets bigger than 2, then we can say well, yeah, we're going to blow up at this point, right? Because 2 squared plus 2 is going to be way bigger, and you know at that point it's going to blow up. The interesting stuff is when you're less than 1, because then, you know, sometimes squaring makes values smaller at that point. So let's make this change to our escape function. And now if we look at this, right, so our escape count of 1f0 is 2. Our escape count of 1.0 is also 2. Our escape count of 1 is also 2. That's great. So now we have consistent answers for equal inputs. That is nice. I still think that there's probably a problem here with our integers if we get bigger at some point. And, you know, 2 works just fine. 3, that works fine. 4, that works fine. Let's do a bunch of values here. So let's try, you know, say 4 to 10 maybe. Is this gonna, oh, that gives me all 1s. Okay. What about to 100? Okay, it's working okay. I was thinking I might end up with a problem at some point. This is what I get for going off script in a live demo. Okay, maybe we're okay. It blows up in one iteration. The part that I wanted to just alert you to was just how integers work when they get pretty big. So if I have, you know, we have, just to go back to that f of x, or f of, you know, 10, for example, right? So this is 10 squared plus 10 is 110. 100 squared plus 100 is, you know, 10,100. 1,000 squared plus 1,000, you know, 10,000 squared. 100,000 squared. Whoops, let's keep just doing it like this, right? This is all looks right? We're doing just fine. We keep going. This is sensible. Keep going. What happened? Suddenly we got gibberish. And the answer here is just that Julia's integer arithmetic uses, it overflows. So it's a 64-bit number, and if you get too big, if you get over the maximum value of this, so when I square this value here, it is bigger than what can fit in an integer. And you can get a sense of this if I put this in a floating point number. Floating point numbers can happily represent 1 times 10 to the 20th. That works just fine. But the maximum value of an integer, I can actually ask that, right? That's going to be the type max of an int 64, right? We'd ask what the type is. This is the maximum value of that. And that is slightly less than, you know, if I put it in a floating point number, it'll give me the representation in scientific notation, 9 times 10 to the 18th, right? And so 1 times 10 to the 20th is bigger than that, we overflow and we wrap around and end up with some funny numbers. And oftentimes you end up with negative numbers as well. If you keep going at some point, maybe. Yeah, there we go. There we got a negative number as well. It's just, looping through all the values and giving you gibberish. So something to look out for. Often doesn't end up happening that much after you start learning Julia. It's like a first thing that you do is like, let's put this language through its paces. Let's get a really big number and explode it. And that you get the wrong answer. It feels like the wrong answer. But that's what's happening. You can still evaluate this in Julia. You just have to explicitly opt in to a larger precision type. And you can do that just by using the big function that will give you arbitrary arithmetic. And now you can, have as large of a number as you want at this point, and it'll happily, give you the correct answer at arbitrary precisions. And again, big, just a name of a function that automatically promotes to a larger precision type. And all through this, I'm using the word types, right? We're talking about types. We're looking at types. We've introduced the names of some types. We've talked about, there's float 64, there's int 64. These are all just names of types that are, the values that we're working with. And so that's, yeah, I think that's all I want to say at this point about types. Great. Any questions on, what we've did there? We changed our definition of escape count to look at, a threshold instead of is infinite, because not all types represent infinities at the same levels. So now we have a consistent thing, except for, if you use a really large integer, you might get some funny answers because it might overflow. Yep. That's a great question. So the question is, I have this big integer, right, which is, let's call it my I is big, this thing, right? I can ask for what is the type of I. And the question is, if I pass I to a function that doesn't need all that precision, does it automatically scale down, right? Or perhaps more notably, if I, just say a big 3, right? Like a 3 itself doesn't need variable precision to it can be represented as a hardware, 64-bit integer that is fast on our processors. Is it still going to be a big integer? And the answer is yes, right? Like I've explicitly asked for 3 to be a big integer, and that's useful for a number of reasons. One is like I might want to take I to some really large power, and because it is a big integer here, it's funny, it doesn't. I may have overflowed my buffer. It went too big. There you go. It evaluated it. It just wasn't happy printing out. However many numbers that takes to do, right? And so the reason that it's useful for it to always be this type is because I might want to do some operation like this, right? Where I'm taking it to a big value. So whether I pass it to a function or work with it, it's always going to be a big integer. And that is its type, and it's not going to automatically, shrink down to a precision that's more efficient, right? You have to explicitly do that.
So then you have the function that you want to compile down really efficient and optimized.
Yeah.
And it just so happens that you only need 1,000 bits in.
Right.
Will that be like type stable behind the scenes? Will it recognize, oh, I can actually just use, 10 ints next to each other, or will it be an object that makes everything slower?
Yeah, good question. So the question is, what happens if you're writing a function that doesn't need that sort of arbitrary precision? And kind of underlining that is a question about performance, right? Like how can you reason about performance of different things in terms, like there's this underlying assumption that big integers are going to be slower, right? and that's true. That when you're using a machine integer, you're on the fast path. You're using something that your processor knows how to work with. With an arbitrary precision thing, it needs to have the capability of using more than 64 bits, and that's more complicated, and so it takes more processing time. And then wrapped up in that is the question of type stability. And let's talk about that. So we can have this function. How do we want to explore this? Let's call it do math, right? Where yeah, is some value. And let's return value. Let's do the same thing, right? Value squared plus value. No, this is I'm happy to do this little aside because I think it's useful to talk about, right? Because when I call this function, so I just have one generic function with one method, and I can call this function with either the number 3 or the big value of 3, and you can actually see Pluto automatically times the evaluation of everything that you do. And so you can see down here that when I ran this, it took 5 microseconds to do math with big 3. And when I did it with just the 3, it took on the order of nanoseconds, right? It's, what is that, a factor of 100 slower to use a big integer arithmetic? And it's giving me the same answer. So could I make this faster, right? And it's a little interesting to think about how it's able to give me the same answer at a faster time, but that's a question for another time, perhaps. One thing that I could do here is I could say, well, if my value is less than type max of ints, let's say value equals int value, right? So this is that explicit, let's downcast. Let's try to reduce the complexity of the problem. If we can fit it in an integer, let's just say that the value is going to be an integer instead of a floating point number. So if I do math with 3 again, we're still in the nanosecond range. If I do math with big 3, the first time I call it, it might have some compilation time. So let's run it a few times here, get a sense. So now we're down to 2 microseconds. It's still not as fast as doing it with an integer. Maybe it's slightly faster than it was before. But this is getting at an interesting point here about type stability and the way in which Julia gets its performance, which is that, I've not told Julia about types at all. In anything that I've written so far today, I've not said, the type of this is going to be an int64, and that's very much intentional. And it's very much how Julia itself works, is that when you call a function, it takes the value that you pass and asks what type it is behind the scenes, and then calls an optimized function for that type. So when it gets a value of an integer, it sees, oh yeah, so this is always going to be an integer, and it can probably even remove this check because it knows that the value will always be actually less than or equal to the type max of an int. So it can probably see this, and it'll probably just realize, oh, if I pass an integer, this check can be a no op, right? That's an optimization I would expect Julia to be able to do. And so value is always going to be an int64 when I pass an int64. If I pass a big integer here, well, do math is going to to compile a specialized version of the function for a big integer, right? There's still only one method, but now we have actually two specializations of the method. And two, you can almost, for those of you coming from C++, it's like a template. This is almost exactly the same as a template. All Julia functions are templates. And they just get instantiated at runtime instead of compile time, so you don't have C++ template error nightmares. So what's happening is it's getting a specialized thing for value, assuming it's a big integer. But in the body here, now sometimes value is going to be a big integer, and sometimes it's going to be a normal integer, and that's what we call a type instability. And it's just gives a little bit of extra overhead in what we end up compiling, because behind the scenes, Julia needs to be able to ask, on every operation that you perform on the type, it needs to ask, is this an integer or a big integer? And what functions do I call from there on out? If it knows that it's always going to be an integer, it can know to use the integer arithmetic of your processor and do that happily. So this is called type instability. And it's generally a good practice to always have the same types throughout here, and the red flag is that I'm reassigning or changing the name I'm using here to sometimes represent an int 64, sometimes represent a big int, and that is overhead that ends up costing performance a little bit. So yes, you can do it. Yes, it's a little slower. Yes, there are ways to make this kind of operation fast, but I think I'll leave that for another day. Overhead will reach the runtime because it's the asking those meta questions of what type are you and how do I square you that has to happen at runtime if there's a type instability.
Could you
Yeah. So one thing that you can do here is you can introspect your code, and we've not talked about them yet, but there are these things called macros in Julia. They are these fancy things with an at in front of them, and they do fancy things. They're kind of like little keywords. I can ask Julia to give me what kinds of types it thinks is going to happen in an operation. So instead of evaluating do math of 3, I can ask it, hey, what types do you think are going to happen when I run this? And it'll spit out, prints this out, and it gives you kind of somewhat messy stuff in the output. But this is the internal representation, and you can see here it is adding these annotations for me, right? It's behind the scenes when I call this. It's compiling specialized operations for integers, knows what types are going to be, knows that it's going to return an integer, things like that. But if I do a big 3 here, it is going to say, hey, this is a union, and it prints it out in caps, just as this is the Pluto thing that's not printing it quite as nicely as if I was doing it in a console window. But like, this is a problem, right? This union is saying, at this point at runtime, I need to ask, is it an int64 or is it a big int? And so now how do I fix that, or how could I recover from that? Well, right, exactly. Right. So it's not a problem for the integer values. It knows that these are integers, and so this is the fast specialization. It's only a problem with big values that you end up with a problem here. This is really core to how Julia gets its performance. Yeah, Russ. Yeah.
You'll get a big red warning sign saying you are screwing this up.
Yeah.
It's just this display is not.
This display is not as pretty. Yeah, I'm not printing it out nicely, or it's just, yeah, somehow not. I don't know. This is Pluto being funny. The other thing though that you can, so how can you fix this? Well, one way would be, so if value is less than type max of int, like instead of putting this outside here, so at this point, it's needing to ask, is this an integer or is this a big int? If I put this inside here and make an else branch like this, kind of refactor, this is a really simple refactoring, if I spell return correctly. Now it will, still have a type instability at the end, but it should be faster because it's not needing, it knows inside this branch that this is always going to be an integer because we've cast it to an int. Did I confuse you? The return type is still unstable, correct? Because it'll sometimes return. So that ends up being a problem downstream. But in this, for this function, it'll be fast again. I would expect anyways. Let's just see. Second time I run it. Yeah, 1 microsecond. Still not as fast as I would hope it to be. Yeah, I don't know. Yes. Yes, so that gets to the next part, right? So right now we just have one method. We could explicitly say, what do we do when we get an integer? And this is how you define a method that only works on a particular type. Let's make it an int64 just to be explicit. And I can say return value squared plus value, right? Like that. That gives me just one method. And now when I do it, right now I'm saying that this method only applies to int64s and nothing else. So now I'm getting no method matching errors when I try to call it on a big int. And so now I would also have to define a second method for big ints explicitly like this. And now the world is fine again. And now I have two methods, both with one argument. So what we had seen before when we had done methods, we had different numbers of arguments, but now we have methods do math. We have two methods that take two different types. And this can allow you to change, behind the scenes when you don't have types, Julia will specialize, but this allows you to change the implementations yourself. It can be useful for optimizations. It can also be useful just to do something totally different. Yeah. Yeah, right. In this case, like these two things are totally redundant, and it would be much better just to not put types on it at all. And, or I could have, just a simple version here, value squared plus value like that, right? Like now I have a third method that's a fallback, is often the way we talk about it, or the generic implementation that doesn't have types at all. And now if I pass something different, like a floating point number, it would just use that and it would specialize for me. There's no need to do this for performance sake. You only need to do it if you want to do something different, like, downcasting to an integer, or, some fancy optimization that you have that you can handwrite better than Julia can specialize. Yeah, good question. It was a fun alley to go down. Thank you. Okay, so that's on types. I think that's really helpful to think about. The other type that I want to start talking about now, and I don't know if anyone saw this coming, probably some of you have, is complex numbers. So you can do 2 plus 3, the complex imaginary is called IM in Julia. Some languages use I, some languages use J. It's just a complex number, and it's a real numeric type. It has a real part. You can ask for the real part of the complex number. It will just give me the 2. It has an imaginary part, and it'll just give me the 3. And it's a numeric type. I can do things with it. I can square it, right? That'll give me a value. I can add to it, right? I can, add numeric values. I can multiply. I can do all the things that you would expect to do. I can also ask my escape function with it, right? So 0.25 plus 0.25 IM, right? This gives me some value as well, right? It's just works, which is kind of cool. It gives me the numbers that I care about. And what's happening? Well, it's creating a specialized version of my escape count function here, and just squaring complex numbers and adding complex numbers, asking if the absolute magnitude of the complex number is greater than 2. That all works without giving types at all. And yeah, we can just see here the type of this thing is a complex. Now, this is a complex with curly braces. This is what's called a parametric type. And it's just kind of, you can think of it as a flavor of complex. I can also have 2.0 plus 3.0 IM. This is a complex of float 64, or, there's a nice alias for it, complex F64, which I think is probably more familiar to Fortran programmers. But it uses the curly braces. The thing that's inside this curly brace is exactly float 64. And so there's a lot more that can be said about this, but for now, just know that what happens inside curly braces is just kind of like a detail on complex. Complex is the type, and float 64 parameterizes that type to say, hey, this is a complex number with floating point values as its real and imaginary values, or integer values. That's all there is there. So when we had plotted our escape count function with real numbers, right, we got this curve. And the cool thing about escape count with imaginary numbers is that they get way more interesting. Let's create, so how could we evaluate this, right? Now we have an imaginary numbers. What we could do is we could do the same kind of plot, right? So remember, we have our x-axis is, what did we define? Yeah, 0.25 to 0.3. I can do the same exact plot, plot x-axis. And now let's do the escape count of my x-axis. But what do I want to do with it, right? Let's add that with 0.25 IM, right? And first, is this going to work, right? X-axis plus 0.25 IM, and the answer is no. It's not going to work. Why not? We have a no method matching thing here, and now hopefully you can start reading this a little bit better because I've described a few more things, right? We're trying to do the plus operation, the function named plus. We have these double colons, which is prefix for a type. And we have a type named step range length that's parameterized by floating point. So this is a step range, or the x-axis is itself a range of floating point numbers, and we're trying to add a complex number to it, right? So that's the thing. And there's a little help thing here for element-wise addition, use broadcasting. So let's do that, right? So we can do the same thing and put a dot in front of the plus. This will be helpful for, let's see, is that gonna work? There we go. There we go. So this is going to be familiar to those of you coming from Python and MATLAB, this kind of dot plus. It's the exact same broadcast operation that we had done with the escape count here. It's just happening now on the plus. And the slightly confusing thing is that when you do it with an infix operator like this, the dot comes before the plus, whereas down here it came after the function name. you can kind of make this make sense in your mind. Like this is like a dot parentheses operation, right? Like the function call itself is the part that matters. So dot parentheses, dot plus. But this is giving me, taking every point in my x-axis and adding 0.25 times the imaginary component, right? So you have, all of these values are available for me to look at. So I can put that inside my escape count function, which is also pointwise, right? So now all of these things are happening pointwise or broadcasting together to give me a value. And in this particular case, oh, it's not very interesting, right? We are, we're, taking 101 iterations to blow up. So maybe we make this a bit bigger, right? And see, is this interesting, or is, 0.75 interesting? Oh, now we're down to 4 iterations to blow up. Well, that's, and we can keep playing around with this. There's got to be a better way though, right? And there is. One thing that we could do here is, instead of using, just kind of doing a one-dimensional thing, we actually have 2 dimensions, right? We have the real component and the imaginary component. Well, what if we look at a bunch of x's, and let's make this a range from -1, let's do -2 to 1 with 100 element. Let's just do, say, 15 elements right now. This is a slightly different way of doing the colon syntax. It's the range named function. Again, go to documentation. Range is the name of a function that can take 3 arguments: start, stop, and length. And you can say, so between -2 and 1, give me 15 values, and it'll automatically compute what the step needs to be. And it prints it back to me like in the colon syntax, right? So it's just a kind of a convenient way of, I don't want to have to compute what that step needs to be in order to give me 15 points between -2 and 1. So that's my x's. Let's do the same thing with y's. Do a range from -1 to 1 with 15 points, right? And what I'm getting to here is, well, what if I, how can I look at all the combinations of these things together? And what this is also going to be now broadcasting. And you can broadcast, what we've done so far is just like pointwise operations across a vector, taking, adding some constant to a vector, or applying some function across a lot of values. You can do the same sort of thing with multi-dimensional values. And so now we're going to start talking about dimensions. When I write a list in Julia with 1, 2, 3, it prints out just as 1, 2, 3. And it kind of does so in Pluto with a fancy syntax here of, this drop-down reveal triangle, 1, 2, and 3 here. And it does that because this is actually a vector, a column vector, mathematically. We think of the lists in Julia as being columns or column vectors. And if I space separate them, we get rows, or a 2-dimensional matrix with 1 row and 3 columns. And that is how this works. So now if I add these 2 things together with a operation like this, 1, 2, 3 dot plus 1, 2, 3, it does the broadcast of them. Let's make them different numbers of elements to make it a little bit more clear. So the first value here is 1 plus 1. The second value is 1 plus 2. It's kind of doing the combination of everything. Again, should be familiar to those of you coming from MATLAB or Python. This is the BSX fun, or the NumPy's broadcasting, exactly the same. And it's the same operation. It's a pointwise operation, but it does this very clever matching of dimensions to kind of do a product in this place, right? It's doing kind of exploding out to make this happen. And it'll also, make things work if you have 3, it aligns all the arrays and does lots of fancy things, but for our purposes, what we want right now is we want to take our x's, right, and make that a row vector instead of a column. So right now, if you look at type of our x's, it is a, this fancy step range length. It is a vector. It's or size is perhaps better. The size of this is just 15 elements. It's just a tuple with one value of 15 elements. Whereas if you look at the size of this 1, 2, 3, 4, this is my 1x4 matrix, right? And so what I want to do is I want to put my x's along a row instead of a column, because those are going to be, x's. They're my x-axis, or my values along the x side. So how do I do that? One very simple way to do is just transpose it. Now I have it prints out not as a range anymore, but it says that it's an adjoint. This comes from linear algebra. You don't need to worry about what that means. The important part is it's a 1x15, or that the size of it is 1, 15, right? There's 2 dimensions. The first dimension is 1, second dimension is 15. And so that means that I can now add this to my y's, which are still in the column, and multiply that by im, and I get the Cartesian product of all of these things, right? So I have a 15x15 matrix now of my x's along the one side, my y's along the other, and you can see that the reals and imaginaries come from the 2 columns. So in my first row, I have a -1 imaginary value. In my first column, I have a -2 real value, and then it combines everything from there. So now I can do my escape count on Pointwise across this entire grid, right? So it is doing all of these operations, and we end up with something like this. Let's make my y's a little smaller, maybe 10. There we go. So now I have this thing, which, I don't know, is this familiar to anyone? What's this look like? Mandelbrot set. Yes, exactly. So that's what we've been building up to. It's taken us a little bit to get here. We've built up to this. This is the Mandelbrot set. And it doesn't look very interesting though, right? It's just numbers. So how can we make this look more interesting? And the answer here is, let's bring in some colors. So one of the packages that I had you add at the beginning was colors. So you can say using colors. It's available to me. That's what this check mark means in Pluto. Let's bring in the color map function. And let's look at what the color map does. I know a little bit about this function. I can ask for the color map from reds to blues, and it gives me this. You can, again, always double click on a thing, ask for the documentation, and it gives you, all the different things. There are lots of choices that you can put in here, right? We could look at all the blues. It gives me a list of these things, right? But what is this? Like, it's spitting it out as colors, right? What in the world am I getting back from this thing? Let's call it a C map, for just to give myself a name that I can play with. So what is this? What's the type of C map? And here we're getting something that we've not seen before, but I've talked about. It's a vector, and in fact, it's a parameterized vector by this RGB, which itself is parameterized by a floating point value, which is a little bit of a mouthful, but all it means is that I have red, green, blue objects. What's an RGB? Well, it's using colors RGB. This is the name of something. Let's say 0.5, 0.5, 0.5. It prints out as a color swatch. That's what it is. And I can change the values here. What is this thing? What is RGB? Well, it is RGB. It's just a thing that is a color. It's given to us by the colors package. And when I do this, it's a type. It's a type constructor. The first parameter, the first value is the red intensity, the second value is the green intensity, the third value is the blue intensity. So I can understand color swatches, and this is where Pluto is so fun because it knows how to print these things. It knows how to display color swatches. And so instead of just saying that it's an RGB with 0.5, 0.25, 0.75, it can show me the color swatch. Yeah. Yeah. Yeah.
What method is dispatched to be?
So yeah, this is using multiple dispatch at its core, which is, we're not going to get to very deeply, but I can give you a little bit of an insight into how this is ending up happening. What ends up happening within a traditional object-oriented language like Python is each class has methods, right? When you define a class in Python, you have methods inside that class. I've not done any methods at all, like not class methods, but you're still seeing methods show up here, right? I've not defined classes, I've not done things, but we're still talking about methods. Why is that? And the answer is that in Julia, the classes or the data themselves, the structures and the actions, the functions are totally detangled. So instead of putting methods inside of types like you do in Python, in Julia, you define a type and then you decide how you want your functions to work with that type, which is what we did with that do math function, right? We added methods on big int to a function that we defined without reaching into big int, right? And so that is at the kind of core of how we can do things in Julia without building them into the language. You can kind of do the language itself is extraordinarily extensible. So what ends up happening here is that there is, what happens, the display system is kind of crazy and very advanced, but at the core, it's calling a show function, where you say, like, let's show the number 1, and it'll print it out in some way. It's a little bit more complicated than that because it knows whether you're in an HTML capable environment, and there's all sorts of craziness that goes on there, but it's overloading these things. So kind of at the core, somewhere in there, actually, let's just do that. Let's look at methods of show. There are 641 methods for the generic function show in base. And what do these methods look like? Well, they define how you display everything in the language. And this is, decouple outside of the method or the structure definitions themselves, or in Python, you'd use the language of class definitions. So when you define, let's see, there should be an RGB in here somewhere, I think. Yeah, here we go. So when you display in, so this is where I was talking about how the show methods are pretty complicated. Because it knows whether you're outputting to a textual system here, right? So this is multiple dispatch. It's outputting to some input-output argument with a context of a MIME type, which may be familiar to you if you've worked with email or who knows what web systems of a text. So if you're outputting some sort of RGB type to a textual system with text plain, it'll call this particular method. And I can maybe even click on it. See what happens if I click on it. It doesn't work because I'm on Julia Hub. And if you're in a local environment and you click on it, it would open in your like a text editor to show you the definition there. So that's one RGB definition. Here's another RGB definition, right? And there's actually more things, like actually, let's just do color. let's see, there should be a show method for HTML too here for colors. Oh yeah, here's a show method that knows how to spit out SVGs, right? Or, you know, all of these things are overloaded in kind of crazy ways to give you the capability of doing this. So that's a lot of internal details, but kind of gives you the sense of what is possible with this system. And it makes it way more extensible than using magic dunders in class definitions. Yeah. Okay. Let's get rid of that. That's a huge cell. All right, so that's displaying these things. And so in our CMap, right, CMap, remember, was a vector of these color swatches. And similarly, Julia knows how to display a vector of color swatches as like an image. But I can go in and index into this. So the first value here is this deep red. You know, the 20th value is a light red. The 40th value is, you know, a pinky version, right? Like you can see how these things go. You can also use the end keyword to get the last one. So that's our color map, and I can index into it with single values. I can also index into it with a bunch of values, right? So I can grab the first value, the fifth value, the 20th value, the third value, the 34th value, right? So this is using square brackets in two different ways. The first square bracket is the indexing operation, like, hey, let's grab this. The second square bracket is creating a kind of an ad hoc vector of a bunch of values that I want all of them. So I want 5 values, gives me 5 swatches back. Now, this is where it gets fun, of course, is we can grab my escape count, which I have as this 10 by 15 matrix of what? Numbers, right? They're numbers between 1 and 101. Well, those could be indexes into my color map. The one thing I need to make sure of, though, is what is my length of my color map? The length of my color map is just 100, right? So let's fix that. And one way we can fix that is the color map function itself. If I look at the thing, there's an optional argument here, right? You all know how to read this, right? This is an optional positional argument of n is 100, and you can change that, right? So I could say that I want instead 101 values. And so now I have a CMap of 101 values, and I have an array of values from 1 to 101. I'll just copy and paste it so that way it's at my bottom here. So these are my values, and I can index in with a matrix like this, and it gives me a picture, which is cool. It's still not very pretty. Let's make it prettier. Let's grab my X's and my Y's here, right? And let's give me, instead of 15, we'll do 800 X's and 600 Y's. And of course, now I can't see it as an integer matrix anymore, but I can see it as a nice, pretty picture. So this is cool. This is like the reason that I like doing it this way is because it's a very simple algorithm that gets you really complicated functionality and allows us to touch on lots of aspects of the language as we go about doing this. I had wanted to do one other thing here. So let's see, how do we spent more time talking about some other things. So I want to make sure that we get to some interesting parts. One thing that you can do in a Pluto environment that's a lot of fun is oh no, let's skip that. I was going to talk about sliders, but let's talk instead about performance. So that's kind of been at the fore of a lot of what we're doing here, right? And what am I doing when I generate this image? Well, I'm calling my escape function a lot of times, right? Each pixel is doing potentially many iterations, lots of loops, and I've written for loops here. I've just done the naive thing. I've not done anything fancy, but I'm doing this at, how many pixels, right? 800 times 600 is, 480,000 evaluations of my escape function, each of which might iterate 100 times, right? This is like actually doing decent amount of computation, but it is doing it pretty quickly, right? 100 milliseconds. If I reevaluate this, it might even be, oh no, it's about 150 milliseconds to do this entire operation, right? Of all of these things. So it's something significant, but how does this compare, right? Is this a fast operation or is it a slow operation? It can be kind of hard to benchmark across languages. If we go to julialang.org and you click on this high performance link, there are these micro benchmarks. One of these micro benchmarks is actually the Mandelbrot set evaluation. And you can look at the source of this and the GitHub repository. And in here, there's this perf.jl function. This is very tiny for you all, but somewhere in here, there's a Mandel function. And this looks pretty much like what we defined, right? Like this is, it's slightly different, but the same idea. You have a z and you're squaring it, adding some constant. I have it written slightly different how we did it. Max is 80. I wanted to introduce optional arguments and keyword arguments, so I made it a little fancier. It's also using my abs squared here. With a handwritten definition of absolute value. It's using abs squared instead of the absolute value that we did, which is a nice optimization. If you know anything about complex numbers, abs squared is faster. So instead of abs of z is greater than 2, it's the square of both sides. Same idea though. But what's cool about this is I can go back and grab the CSV of these benchmarks. Here are all of the benchmarks in all of these languages. I can grab the raw CSV file. I'm just going to copy this and let's go back down here. Let's download this thing. Let's save the thing as a file name. This will download this CSV file into a temporary file. Again, just the name of a function that takes a URL, downloads it, puts it in a file name, and now it's using CSV. Yeah, actually, we don't need to do that. We'll just use it fully qualified. So when you have a module, you can just say csv.read file name. And we'll want to use, actually, no, we do want to do this. We're going to say using data frames. I'll bring in the data frame functionality. This is how we talk about tabular data. So now I can read a CSV file as a data frame. So CSV and data frames work together quite nicely to give me tabular representation, and it spits things out in a nice, HTML table. But you can see that it didn't quite do what I wanted. It kind of tried to automatically give me a header, but the first row of this is not actually the header. I can explicitly say our header is going to be language, function, time, like this. And again, this is just a vector of 3 strings. I've not talked about strings, but those are strings. Pretty straightforward. Now I have a data frame with 3 columns and our function. I can name it. DF is kind of a standard name to use for this. And let's grab all of the rows. So DF is you can kind of work with data frames in many ways. The sky is the limit here. You can kind of work with it like a matrix in some ways, right? It's 3 columns, 105 rows, lots of languages, lots of functions. I can look at all the rows where my function, right? So df.function is all of these different types, right? I have all of these different sorts of types, and here's my Mandelbrot. user func Mandelbrot. I can ask, is this equal to this string, right? So df.function. This is, again, broadcasting equality. So I get a vector of trues and falses. And I can index into this with this, right? So I can grab all the rows that are our Mandelbrot function across all of our languages and see how long it took to evaluate all of these things. This was run a while ago. It's hard to get all of these different languages running on the same system, which is what's needed for benchmarks. But this is how you get, how you index into these things. You can index with a bit array like this, and the colon here is now, instead of a range, it's a stand-in for all of the things, right? It's like a slice. So all the columns. So these are my times, or maybe let's call it my perf, is this. So how would I plot this? Using plots, there's a bar chart capability. You just say bar, and let's bar our perf.language against perf.time. And we get something that's really hard to read because Octave is crazy slow. Let's make this a little bit better so you can, there are lots of ways to play with, lots of ways to change around how things do. There's an X rotation keyword argument. Makes it a little bit more easy to read what the languages are, right? So that's this. You can go in and see. So let's go back here to the file, how we generated these things, the perf.jl and Mandel, right? So here's the timing that we had, and you can see how many points we looked at, right? So this was we did a array comprehension to run this, and you can see that we had, these were the two ranges that we ran over. So length of this times the length of this one is going to be how many points we evaluated. So there were 546 points. So we could change this around and say, so let's divide by, how many points per second did we do? Whoops, I did a division there and got a no method matching an integer with a vector. I wanted to broadcast. Now we can see how many, points per second did we graph, right? This is now points per second because we had 546 points. These are our seconds, and there are lots of ways that you can reinterpret this, but here you can find, where is Julia? Here's Julia. In this particular case, Julia is the fastest language, with over 10,000 points per second. Fortran and Rust are close, as is Go. In this case, we beat C. A lot of times people think C is the speed of light, but you can actually beat the performance of C. So this is fast. This is great. And a little taste of plotting. There's lots more that I wanted to go into, but I think that this gives you a good taste of the language. Yeah, the last bit that I just kind of wanted to go to is, oh man, we're so close. So one of the fun things to do with the Mandelbrot set is zooming in on these edges, right? And I'm sure you've all seen the zoom of these different things. The other part of this, though, is that we're really close to getting Julia sets, which is where I wanted us to end for the day. So a Julia set is actually just a slight reworking of the exact same Mandel function. So this was how we got the Mandelbrot set, was our X's and our Y's. Well, a Julia set is, instead of, remember what's happening here, we're doing this escape count of these things, and at each point we're passing a single value, and we have that optional argument that is taking that single value. If we give it an interesting complex number as the second argument, we end up with a Julia set. So it can take a second to find an interesting value of, where something is interesting. See if I can 0.25 IM. I think this is, that one's not too interesting, but these are how you get to Julia sets. So how might you find an interesting Julia set? There are, ways of going about this. Let's see if we can get, yeah, here we go. We're starting to get to something that's a little bit more interesting, right? So you can kind of go around, play around with this. These are all Julia sets, and finding an interesting one to look at is kind of a fun game. And you can find it in exactly the same way that we did with the Mandelbrot set, right? So I started by playing around with single values, but how might you find an interesting value? Here's where I'll do one last thing. There's using Pluto UI slider and bind. This is a little bit of Pluto magic. Oh, the bind is already available in Pluto, where you can tell Pluto to bind a value to some picker, like an HTML picker. So let's do 0 by 0.001 to 1, like this. And this is going to give me a value of imaginary that's picked by this slider. I can say show value as true. And now I can do match times IM. And now I can go along here and find interesting Julia sets. So this is what's possible when you have a fast language. This is something that you couldn't do if it took forever to evaluate these things, right? And kind of the magic of Julia that I want you to take away with is for loops are fast, right? You can do lots of really cool things just because the language is itself fast, right? If you were spending, 20 minutes to evaluate each one of these things, you wouldn't get anything near this. And just like you can put this slider here for the imaginary part, you can do the same thing with the real part. The exercise that I was going to have you do is to start thinking about how you could write a function that would automatically find these interesting points. So the interesting points happen to be on the edge of the Mandelbrot set. So, if you want to have an exercise and find me later this week, I'd be happy to play around with you on it, is finding a way that you could, automatically take a random point and work your way towards the edge here, and then, get an interesting Mandelbrot set. Of course, sky is the limit. I hope that this gives you a little bit of an intro to the language and kind of gives you the sense that you can understand everything that's going to happen this week. It's all about naming, all about, evaluating functions and doing fancy things with it. And yeah, best of luck on your Julia journeys. Yeah, I'm happy to stick around. If you have questions, you can come on up and we can, I want people to feel free to go grab lunch and leave the room, but I'm also happy to, keep taking things. I think we should probably, I'll stop the recording. Yeah, okay. So yeah, folks have questions, I'll take them now and we can, please feel free to stick around. I'll stick around for at least 15 to 20 minutes here.
That you've made a definition.
Yeah.
I didn't find that earlier. But when you reevaluate it, they erase the previous definition.
Yeah.
How's it doing it? And why?
So Pluto itself is tracking all the things that are, it is reading the cells and identifying the names that you assign in them, and then keeping tabs on that. And that's a Pluto thing. It's like part of the infrastructure. Mhm.
Delete the any part. But then what if you instead you had F that takes anything, but then you delete that and then you make a new cell that F that has the special type. Will Pluto still erase the previous definition?
So that is like kind of depends on how, yeah, it's a good question. I think it would. So yeah, we can just kind of say, right, so f of x is an int is, got an integer, right? So you have this, and we f of 3, we got an integer. But so now if I do f of x is an int again, what happens? I'm not sure what Pluto will do. Oh, it does. It complains that there are multiple definitions. This is a Pluto error message in the Julia language itself. So if I am in the terminal here, I can happily do this again. Right, and it just reevaluated it, and now it's something else. This is something that is a little bit funny. There's this concept of if I had run this if I did this way and then ran that and then did something else and then ran it again, right? The world state has changed. You can kind of think, right? Well, the world that Julia knows about changed along the way. When it did this, the methods were different. And so there's this concept of the running code that you're running will always see the state of the method tables when it started running. This is called a world age sort of thing. And so what's actually happening behind the scenes when you define a new function like this, it's not actually erasing the old one. It's kind of just saying, hey, the state of the world has changed and now new code that runs will get this value. It only ends up ever causing problems if you're doing persistent deployed applications where you like have some code that's running and you're iteratively updating it. The code that was running will only see the state of the world when it started running, and subsequent updates won't affect it unless you like do some magic about, hey, I want to update the state of the world kind of thing. Yeah.
Maybe more generic ones. Say the top one works on any.
Yep. Or yeah, this, right?
I mean, if it initially ran with so say the top one is any, run it would say something.
Right. So the top one is any got. Yeah. So the second one, right? So this f of 3, it's complaining. It's not happy. Right. So, right, it does this. And kind of the way that you can think of this is when you look at the methods of f here, there are, it sorts it in order of specificity. And so the most specific thing, it'll find things in terms of what is most specific. And you can kind of think of it as walking your way down this list. And it's maybe more interesting if I look at a bigger method table like plus, right? So plus has lots of specializations on it. And it starts with the most specific thing. And so, yeah, there's a lot of them. The most specific thing that's here, dates, and then how do you add matrices and things like that. And then down at the bottom of this list are the most generic things, right? Here's the generic definition of arbitrary nargs. You can add multiple arguments and it does the binary thing along the way. Or, adding unions of dates and things like that. Like there are more abstract types that end up at the bottom of this, in addition to anything. Yeah.
So, in theory, the order of a definition of the function should never matter.
Doesn't matter.
So what if I did, I define a function f of just int, but not int64.
Yeah.
And then I call like f of 3.
Yeah.
And so behind the scenes, an int64 definition will get this.
So
And make it separate.
int is itself just int64. It's an alias. So there is a type called integer that is the super type that is kind of like, see, can I ask for subtypes? Yeah, I can ask for the subtypes of integer. This gives me all the subtypes here. Subtypes of signed. This will give me my, int. There's my int64. So yeah, int is int64 because it just is a shorthand for Julia can run on 32-bit platforms as well. And like the int is the size of a pointer.
But in what I described, there'll be two backend definitions for int64. So you define something that takes anything, let's say.
Yeah.
And then the user calls that passing again. So a compilation for int64 will happen. And now there is an int64, assembly tree. And now then after that invocation, after that function, so the function will have even single. Now you do an int64 specific definition. That will conflict with the existing machine code.
Let's use G. I also used G.
Yeah, and then you evaluate it for an int right away.
Right.
How do you know behind the scenes there's an int64 definition for that? But now you define H with type annotation of so now the original, after you run it, is the original H definition inaccessible now?
For int64s, yes.
Yeah.
Yeah. So Pluto automatically reevaluated this cell because it knows that that was dependent. But if I did the same thing at a REPL here, maybe this will be, right, so got an int64, and then I define my special int64 method here, right, and I do h of 2 again. Now this is the special one. So after I've defined this, I can no longer access the generic function. I could, if I want to do, you can get this if you want to invoke h with, I forget the syntax here. You can explicitly ask to invoke a specific function with specific types and arguments. So yeah, I invoke h with the types of anything and the value of 2. There we go. Now this, yeah. Great. I already let everybody go. Nobody wanted to leave.
I thank you for your help. Please, help with your stand up, and then maybe you don't want to just walk up here if you want to ask more.
Yeah, it sounds
Let's do
good.
it like this. Yes.